Hello and welcome back to Atomic Math. Today we're going to look at vectors because physics is not just about numbers. Physics, it's about describing the world around us. If I was to tell you that a car is traveling 60 kilometers an hour, have I completely described its motion? No, not quite. Maybe the car is traveling 60 kilometers per hour east, or maybe it's traveling 60 kilometers per hour west, or possibly even 60 kilometers per hour north. When I say 60 kilometers per hour, I'm only giving you a size. I'm only giving you a magnitude. I'm not telling you the direction. So we can see that a number alone is just a scalar. But a number with direction, that's a vector. Consider this. You leave your house and you walk 2 kilometers north. Then you turn and you walk 4 kilometers east. And then another 1 kilometer north. If someone asked you how far did you travel, you would automatically tell them 2 plus 4 plus 1, that's 7 kilometers. So your distance traveled is 7 kilometers. But displacement is different. Displacement doesn't care about how you got there. It only cares about where you started and where you finished. So displacement would be this vector right here. And this includes both magnitude and direction. 2 kilometers north, 4 kilometers east, 1 kilometer north, and of course we can combine those and just say 3 kilometers north plus 4 kilometers east. So we can see that displacement is not the same thing as distance traveled. Displacement is a vector, where distance traveled is only a scalar. It also doesn't matter the order in which you put these vectors. As long as you do 4 kilometers east, 2 kilometers north, and 1 kilometer north. You can do them in any order you want, you will still end up in the same location. And once we arrange this like this, you should recognize something. You should see a right angle triangle. And that's why we use trigonometry when it comes to vectors. So just a quick review, our right angle triangle, we have our hypotenuse, opposite, adjacent. And we know that the sine of the theta is always going to be opposite over hypotenuse. And cos theta is going to be adjacent over hypotenuse, and tan is going to be opposite over adjacent, or sine over cos. So how does this help us with vectors? Let's put this on a graph. We can see now that the x-axis is actually what we were calling adjacent, and the y-axis is what we were calling opposite. So we can rewrite our equations to say that sine theta is the y component over the hypotenuse, or rearrange to say y component equals sine times hypotenuse. And we can do the same thing for the x component and rearrange that to say that the x component is cos theta times the hypotenuse. So we can use trigonometry to take a vector and break out the pieces that make up that vector. And those pieces are called vector components. If we take a closer look at a vector, we can see that all vectors can be described in terms of their components, their x and their y component. And to describe these vectors, we use something called unit vectors. They have a length of 1, but they tell us a direction. And for the x-axis, we use the I vector. For the y-axis, we use the j vector. So we can describe any vector in terms of these two unit vectors. Now in this video, we're only working in 2 dimensions, so we're not using the third dimension, the z-axis. But if we were, the unit vector for the z-axis is k hat. So let's take a look at how this would work. Let's put up a vector here and we'll create our component vectors. So remember, each one of these vectors is just a unit 1, but it is telling us direction. The blue ones are telling us y direction, the pink ones are telling us x direction. Now we can see that our vector can be described as 4 vectors in the x direction and 2 vectors in the y direction. So that would be 4i plus 2j, and that's how this vector would be described. We can also add vectors together, which is what we were doing in the first example. Suppose we have this vector here, 2i plus 3j. Meaning it has 2 in the x direction and 3 in the y direction. And then we'll take another vector, which is 3i plus 1j, meaning 3 in the x direction and 1 in the y direction. Now, in order to add these together, we simply move one of them to the end of the first one. So as long as they're lined up head to tail, your resulting vector from adding these together will be the vector that's drawn from the beginning to the end. Now we can see that we could describe this resultant vector in terms of 5 I vectors and 4 j vectors. So we could say that the vector a plus b is going to be 5i plus 4j. Now this is the graphical method, but we could also do this in an algebraic method, which is actually simpler, but the graphic method is better for understanding and seeing what's happening. But if we just look at our 2 vectors, a and b, if we added together the I components and the j components, we would get a vector that has 5i and 4j. So you can see we get to the same place, it's just a different method. And as I mentioned at the beginning, the order in which we add these vectors does not matter. Suppose I added these vectors in this order. order here. My resultant vector would be this green vector right here. But if I change the order of these vectors, I would still get the same resultant vector. So let's try that. Let's just take a look, and we will randomly re-put these together in a completely different order. You can see that the shape is completely different, but the resultant vector is still the same. Let's start by taking a look at an example. We'll start with this vector here. It has a magnitude of 10, and its theta is 30 degrees. So we know that we can use our trigonometry to find the components. So our x component is going to be cos theta times hypotenuse, and our y component will be sine theta times hypotenuse. If we plug that in, we're going to find that our x component is cos 30 times 10, which is 8.66, and our y component is sine 30 times 10, which is 5. So our vector is actually 8.66i plus 5j. Now suppose instead of being given a vector with a magnitude, you were given the vector in its component form, but you wanted to know how long the vector was. Then we're going to use something called Pythagorean's theorem, which basically says that for a right-angled triangle, a squared plus b squared equals c squared. And so we can use this to find the length of c, which is the length of our vector. So c is just going to equal the square root of a squared plus b squared. Now to find the length of a vector, this is the symbol that we use for the length of a vector or the magnitude of the vector. We're simply going to use this a squared plus b squared square rooted. Only in our case, it's going to be 8.66 squared plus 5.00 squared, which is going to give us 75 plus 25. And then once we add that together and square root it, we're going to get 10. And indeed, our vector did have a length of 10. That's what we started with. So you can go in this direction as well. You could also find the angle if you wanted to know what angle the vector was sitting at. We can use sine theta is opposite over hypotenuse, which we now know is 5 over 10, and this would give us 0.5. And to find the theta, we just take the inverse of 0.5, and we would find a theta of 30 degrees. So as long as you have two pieces of information, whether it be the vector components or the length of the vector and an angle, you can find the rest of the information. So let's just review quickly. Scalars. Temperature is a scalar. Mass is a scalar. Distance is a scalar. Velocity is a vector. Force is a vector. Displacement is a vector. And you can see the difference. The scalar is telling us how much, but the vector tells us how much and where. Vectors are the language of physics, and almost everything you'll study in physics speaks this language. In fact, once you understand vectors, physics starts making a lot more sense, and not because it becomes easier, but because you have learned the language it is written in. I hope you liked this video. I hope it helped you with vectors. If you liked it, go ahead and hit like, and if you want to see more videos like this, hit subscribe, and I will be putting out more videos on vectors coming soon with things like the dot product, a cross product, and then eventually we will get into vector calculus. See you in the next video.